66 million years ago, an asteroid the size of a city hit the Earth. And, well, that was it for the age of dinosaurs. Figuring out the physics of that single day is absolutely key to understanding how one rock could kick off a global mass extinction. So today, we're going to dive into a new attempt to digitally rebuild that very event, pitting a brand new modeling technique against the reigning champion. The question is, how on earth do you even start to do that?
Right? How do you build a virtual time machine to witness the most famous or infamous impact in our planet's history? It's an absolutely monumental challenge. We're talking about simulating forces so immense they didn't just shake the ground, they literally reshaped the planet and the entire course of life on it.
You know, the best way to think about this is like a forensic investigation. Scientists are basically treating this as the ultimate cold case, using these incredible digital tools to piece together all the evidence from a 66-million-year-old crime scene.
And this is that crime scene, the Chicxulub crater, buried deep under Mexico's Yucatan Peninsula. And the scale here is it's staggering. We're talking about a 200-kilometer-wide scar on the Earth's surface, left by a 10-kilometer-wide rock, moving at over 15 kilometers per second. And it's not just some simple bowl in the ground, it's what's called a complex crater, with multiple rings, kind of like a bullseye. And that specific feature has been incredibly tricky for scientists to replicate.
So, to try and model this kind of cataclysm, scientists have relied on one particular technique for a long time now. It's really been the reigning champion of impact simulation, and it's all built on this one really powerful idea about what happens when that much energy gets released all at once.
That method is called hydrocode modeling. You see, the energies involved here are so extreme, so off the charts, that for a split second, solid rock behaves just like a liquid. So what these models do is they essentially treat the entire event like a colossal splash in a pond, following the rules of fluid dynamics.
So you've got the established standard, the heavyweight champ, which treats rock like one continuous fluid. But as you're about to see, a new challenger has stepped into the ring, and it has a fundamentally different idea about how to model the ground itself.
And here it is. Instead of looking at the ground as one big liquid blob, this new approach looks at it through the lens of particle physics. It breaks the whole problem down into millions and millions of tiny pieces.
It's called the distinct element method, or DM for short. Now, I want you to imagine the Earth's crust isn't a fluid, but a giant sandbox filled with billions of individual marbles. What DM does is it calculates the interactions between every single one of those marbles, how they push, how they pull, and how they slide past each other. It's a completely different particle-by-particle approach.
And this just lays it all out perfectly, doesn't it? On one side, hydrocodes see a continuous fluid, a splash. On the other, DEM sees a huge collection of separate particles, a collision in a sandbox. So the big question the researchers wanted to answer was, which one of these models gets us closer to the real Chicxulub crater?
To find that out, they had to build their own virtual impact zone and just run the experiment. So let's take a look at how they set the whole thing up.
Okay, so first, they digitally built the ground itself, and they used real-world drilling data from the crater to create 9 distinct geological layers. Pretty cool. Then, they built their 10-kilometer digital asteroid out of bonded particles. They plugged in their variables, and then they just hit play and let the laws of physics do the rest.
Now, the two crucial knobs they could turn here were the impact angle and the velocity. They tested everything from a straight-down 90-degree slam to a much shallower 30-degree glancing blow. And they did it at speeds from 12 all the way up to 20 kilometers a second, all to find that one perfect combination that best matched the evidence we see today.
So, after running all these virtual apocalypses, what did the new model actually show us? What was the final verdict in this showdown, hydrocode versus DEM?
Well, when you look at the numbers, the results were really fascinating. This table shows something called the mean squared error. Now, don't worry about the math. It's just a way of measuring how different the simulated crater is from the real one. All you need to know is a lower score is a better match. And look at that. The DEM model scored significantly lower. That means its final surface shape was a closer match to the real thing than the previous models.
This chart just makes it crystal clear. When you're measuring how well you match the final shape of the crater, the new challenger, the DEM model, actually outperformed the old champion. But, as it turns out, the story is not quite that simple.
Because here's the twist. Even though the overall profile was a better statistical match, the DEM simulation failed to create that complex structure of the real crater. It kept producing a simple, bowl-shaped crater, completely missing those iconic inner rings.
But, and this is a huge but, it did something absolutely remarkable. The model nailed what's called the uplifting effect. This is a key process where the impact creates this incredible rebound, suctioning up material from deep within the Earth's crust and pulling it towards the surface. It's a fundamental piece of the physics puzzle you need to form a complex crater, and the DEM model got it right.
And that is the real takeaway here. Scientific progress isn't always a clean knockout punch. The DEM model didn't give us a perfect picture of the crater, no, but it successfully simulated some of the crucial mechanics that other models have struggled with. It's now a powerful new tool in the scientific arsenal, and the next big step is to refine it until it can form those complex rings.
As the researchers themselves put it right in their conclusion, this isn't the end of the story, it's just a very, very promising beginning. They've proven the potential of this new method, and that opens the door for future simulations to get us even closer to recreating that fateful day.
It really makes you wonder, doesn't it? If we can build a virtual sandbox that gets us this close to recreating the death of the dinosaurs, what other ancient mysteries, here on Earth or maybe even on other planets, could these incredible new tools finally help us solve?